All right. Today let's look at single element studies. It's not really specific to a code, but I'm gonna go over the basic setup and the purpose and the overview of single element studies, and then I'm also going to showcase basically the as many of the low cases as I've ever looked at in the past. I think for each of these low cases, not every material model is necessary for each low cases, but these different low cases basically generate different kind of stress state, and based on these stress state, obviously there is different reasons for having each of these stress states. So that's the purpose for having each of these low cases looked at. So I'm gonna go over the overview first, and then I'm gonna look at the different load states. And I have sort of files already prepared, which I can sort of share with you. Some examples that I've generated, why I look at all of these different kind of results. Okay, let's get started. Um, A single element study is basically exactly as the name suggests. It's usually like a 1 by 1 by 1 cube. So in my case, I use the millimeter ton second units systems. And in that regard, I'm gonna have a 1 millimeter by 1 millimeter by 1 millimeter cube. And this cube is gonna be meshed with a single element only, right? So that's where the name comes from. It's a single element study. Usually this is a linear element, so we don't have any missile node. That doesn't overcomplicate things when that happens. So it gives you a very easy way to support the different. There are different nodal constraints for the a noded element, and then there are different loads we can apply on the a noded element, and then we can essentially evaluate the implementation of, say, for example, a material model based on a specific stress state. Say, for example, uniaxial tension. We can basically evaluate that as a function of the displacement that's applied in the normal direction, and we can look at what the strain will look like, and that gives you that stress state that you can use to compare to the actual test results, right? So it's a way to look at to verify how well a material model has been implemented into the code, because the material model came from a physical test. It's calibrated into the material model. Because it's calibrated into the material model, if we were to model that test with a single element, the results should line up, right? Because you can think of it like a back and forth. Material model comes from test. Material model can be used to model the test. The test and the simulation should match up relatively well to know that the material model has been correctly implemented into the code. It can also be used to test our element formulations, right? So for a simple model, you have a standardized element formulation you can use. There are other models that are more complicated in terms of its implementations, and it requires different kind of element formulations. And that's also where we can input the correct element formulation to make sure we'll have the correct modeling choices being made in terms of what element we're using. Okay, and the key word here is verify, right? So I took this snapshot from ASME VMV40 slides, but basically verification is a way to look at the model implementations, right? So it's essentially trying to look at how we're solving the equation in the background, right? So when we talk about verify a model, we're always verifying the actual equation that we're solving in the background, right? So when we use the right material model, when the right material model is implemented correctly, we're solving the equation in the background with the correct stress strain curve, for example, right? Whereas validation is a much more holistic way to look at a specific applications, right? So verification is never targeting a specific application. It's targeting the verification of its implementations, whereas validating is always validating towards some reality of interest, right? So when we talk about validations, we're always validating towards something that we can physically test, we can physically measure, and it's about implementing the finite element model as a whole, and how well does the holistic model represent reality, right? So verification is much more internal to the logic of the code, whereas validation is much more external to the actual application itself, right? So that's a very important distinctions. I like this slide a lot, especially first two bullet points. So understand the difference is important, because single element study is always a model verification, right? We're verifying the implementation of the material model. Okay. All right. Going from there, really, like if you look at a basic single element study, the way I drew this is that you have node 1, node 2, node 3, node 4, node 5, node 6, node 7, node 8. Each of them has a coordinate. So this is the origin, and then this is 1 millimeter in the x direction, this is 1 millimeter in the y direction, this is 1 millimeter in the z direction, and so on and so forth. Right? So basically, I have a nodal brick that has these specific nodal coordinates. These nodal coordinates, obviously, right, correspond to the node locations, but it also has a specific constraint that we'll want to apply to it. So the way I'm going to discuss single element study, right, as a summary, because of what I like for this video and these slides to be about, is a repository of how to do single element study as a summary, so people can come back to it. I can come back to it even to remind myself how to do this, so what the constraint is actually going to be for each of the load cases. Okay, so what this table does is that number one, there is no rotational degree of freedom because this is a solid element. And then for each of the x, y, z translational degree of freedom, for each of the nodal locations, I have the indication of whether or not it's going to be a constrained, or it's going to be free, or if it's where the load is applied. Okay. Don't worry about this actual setting here. I think this is like a placeholder I used. But for overall, this is basically how I'm going to describe as a summary for how to do the single element study is essentially for each node, I'm going to describe the constraint applied to that node. Whether or not it's going to be constrained in that degree of freedom, whether or not it's going to be free in that degree of freedom, or whether a load is applied. When a load is applied, it's basically moving that node in that specific direction. Okay, that's what it means. All right, so when you have a load, it means that node is being required to move by the model setup in that specific directions. Doesn't matter how much it is, it's being moved. So in a way, it is also a constraint, but it is in essence a boundary condition. It's moving that node in that direction to generate the strain in the elements, and then allow us to calculate the stress. Okay. All right. So let's look at the different load cases. Uniaxial tension basically look like this, right? So you can sort of see it's just extending the element. And if you look at the constraints, basically it's in XYZ plane. So I can show the real quick in the actual model for uniaxial tension. It's going to be right here. No, actually, 1 second. Where's my uniaxial tension? I should probably just fold each of these analysis systems until I find it right here. Okay, so if you can sort of see, this is the origin, right? This is my 0, 0, 0. This plane is going to be constrained to the z direction because it's essentially a planar constraint. Planar constraint in the y direction, a planar constraint in the z direction. So when you have these three plane constrained the way they do, right? You can sort of see this basically puts this one at fully constrained. Everything else is just a step away from that. And then what you also have is a phase that's applied in tension only, right? So you're basically moving. So when you apply a displacement on that surface, you're basically moving all four nodes on that surface, okay? In that direction, in the x direction by 0.25 is what's happening. So if you follow all of that, what I did here, this is a much more indirect way, but some code require you to define the nodes by the XYZ constraints. So it's not going to be as easy as a workbench. Workbench makes it easy for everybody. You just have to assign some surface level constraint and you're good to go. Some other code like Dyna, for example, will ask you to constrain the nodes individually. In that case, you can sort of see the basic constraint that you're doing is if you follow the 0, 0, 0, 1, so I basically rotate this way and rotate this way as you go down the list. So you can sort of see this one has a load applied to it, but it's also constrained in both the y-axis and the z-axis. Right, so this one can only move along the x-axis. Is essentially what it's doing, and when you can sort of see this kind of constraint is applied, right? So you see this node right here is allowed to move inward a little bit. That gives you that little bit of a Poisson's effect. Okay, so that's uniaxial tension. Uniaxial compression is the opposite of that, basically. So you can sort of see it just goes the other way. All right, pretty standard. So these two have exactly the same constraint because uniaxial tension compression just opposite to each other. Bi-axial tension, bi-axial compression is the same thing. Bi-axial tension just goes two different ways, right? So in this case, what you have is you have. So let's look at it in the actual example, right? So this is uniaxial tension, uniaxial compression. Let's look at biaxial tension. It's right here. So what you have here is still that these three surfaces constrained along the origin, and you have a face moving that way, and you have a face moving that way, right? So you can see these two faces moves out this way. Maybe this is a better way to look at it. Let me rotate it a little bit. Okay, so this right here, that right there, and then you have these three plane being fixed in place, and that give you the tension in two different directions. And then you can sort of see in uniaxial tension, my I actually plot a triaxiality down here. Triaxiality is 0.33, right? This equation right here bases your hydrostatic over your von Mises, give you the triaxiality. I give you a 0.33 uniaxial tension, uniaxial compression, give you the same triaxiality of 0.33, right? Negative 0.33 in that case. And then obviously biaxial tension, biaxial compression is going to be 0.66, right? So this is negative 0.66, and this is positive. Down here is going to be positive 0.66 right there, right? So this gives you the correct. This is also how you know you're constraining the part correctly, right? Giving you the correct triaxialities. So in this case, you have uniaxial tension, and in this case, you can sort of see this is all free along z direction. For the top 4 nodes, is because of the ability, because you need to do the biaxial tension. Same thing with the biaxial compression, it goes the other directions, right? So pretty standard, right? So this is actually really hard to follow. So as part of me making this video, I realized how difficult it is to follow all of the constraints. Which is why I made the table, because once you make the table, once you have the coordinates, you should be able to map it based on the table. So the way you can use these slides is to look at how the location is a constraint, right? And then you can sort of just say, based on each of these nodal collections, I know exactly what kind of constraint I should apply to get to these results. In the workbench side, they make it a little bit easier for you. But at the same time, it also convolutes the vision of exactly how to constrain it. But it's something to notice. Now, pure shear is exactly as it sounds. You just put this into a pure shear, right? So you're fixing the bottom two surface, and you're allowing the top surface to go. And all of the y is constrained in this case. And what you're having here, so if you look at the pure shear conditions, if you've got a pure shear conditions, right? So your triaxiality is going to be near 0. So this is basically a 0 triaxiality. You basically don't have anything, and this is a pure shear that you're applying here, as you can see. Maybe that's not good. This is a better view. Yeah, sorry. There we go. Right. So you're gonna be able to say you have 0 triaxiality of 0. This is how you know you have the correct pure shear condition, and all you have to do is fix the bottom surface and then allow the top surface to go. And you're also constraining any outer plane, so you have a pure planar tension, planar shear across that top surface, and that's how you have the uniaxial compression, the single element study. You know, this stress state, obviously, if you're building a model with overlap shear, for example, you can use the pure shear as a verification method. Usually people don't do that, but that's an idea. Now, volumetric tension and volumetric compression is the opposite, right? So these are two opposite. Basically, in this case, you are essentially testing the bulk responses of the structure. So you are applying the load to generate a volumetric change only, right? So in this case, it's actually really interesting. Let me show you. So volumetric compression. I've never done a volumetric only test, other than single element study. So you actually have a 0 von Mises stress. Right? You see your von Mises stress is completely 0. Because all you have is the volumetric component of your stress tensor. You don't have any deviatory component, so you have no von Mises stress. And your triaxiality it says it's 0, but it's actually infinite because you're dividing by 0. This right here is actually 0. I don't know why it says 0 here, but it's basically infinite. So the triaxiality doesn't really compute here. It doesn't really apply, I suppose. And then what you have here is just exactly what you see here is just a volumetric. This is a volumetric compression. And then over here you have the volumetric tension, which is like this. Oh, this is compression and this is tension, right? In this case, what you're doing here is that you're basically the same constraint on 3 surfaces, and the other 3 surfaces are allowed to expand outward, and you're basically doesn't have a single degree of freedom as being free. Everything just applying a load, so that's why you have it in sort of a uniform expansion outward, right? And very lastly, you have the planar compression, which is very similar to uniaxial compression. Except in this case, you're allowing, so if I compare this versus a uniaxial compression, right, I'm basically constraining that y degree of freedom in the other 2 nodes. So the nodes on the other side of this face right here, so 1, 2, 3, and 4, those 4 nodes, instead of having y degree of freedom being free, you are constraining that Poisson's effect. In this case, so all of that become constrained. So what you have is a planar compression, right? And this planar compression gives you a way to sort of look at that specific stress state. No, one thing that you can sort of test, right? So in this case, what I have is a simple steel material, right? This is a test material, which is basically just a steel material with a yield strength of around 300. So what you do here, if you look at, say, for example, uniaxial tension, what you have here is, you know, a load, linear ramping load until reach 300 stress, and you just flats out. And if I look at my normal stress, it's the same thing. Normal stress, shear strain, normal strain, right? So this is my normal stress because all I'm applying is a normal stress in this case, right? You can also check for, in this case, I have a rubbery material, right? So in this case, I have a rubber material. This rubber material will have a stress that look like this. So in this case, what I have, I think is just, I don't remember which one these came from, but basically it's a stress strain curve. You can sort of see it just, you know, gets stiffer and stiffer and stiffer, follow a hyperelastic curve. And that's basically how you can verify, depending on how the hyperelastic curve is generated, you can test, because hyperelastic curve are generated based on some combination of these tests, right? So they might have a bi-axial tension, bi-axial compression, they might have volumetric compression. However test is being used to generate the material model, you can use that specific stress state to verify that material model is correctly implemented by comparing that to the test results. And that's how you can use a single element study. Okay? And right here, if you use these slides, just follow the slides, follow the video to look at the specific constraint and loading conditions. It's a very good summary in my mind. It took me a while to put this together, by the way. It's actually extremely confusing to do this. And I have a spreadsheet made right here, just to show real quick at the end for each of these load cases. And that's how I'm going to track it for myself in the future. The template helps, but this kind of table helped me do single element study in other code as well that doesn't use Workbench, for example. Okay, that's all. Thank you very much. I'm hoping this is helpful. It's a very simple video, but I think having this summary as a repository is going to be very helpful in the future. All right, thanks. Bye-bye.